Hello and welcome to my presentation from DQN to R2D2. In this presentation, I'll be talking about how DQN or Deep Q networks, a reinforcement learning algorithm, has evolved over time to give rise to more powerful and robust deep reinforcement learning techniques like the R2D2 agent, which stands for Recurrent Replay Distributed DQN. I will start off with an intro to RL and then gradually work our way up to a high-level understanding of the R2D2 agent. So this is a timeline of how DQN has evolved from its inception in 2013 to 2019. There are of course many other improvements made to DQN, but these are the papers that are directly relevant to understanding R2D2. In 2013, DeepMind published the seminal DQN paper, and in 2015 there are Recurrent DQNs, Prioritized Experience Replay, and Gorilla, which is a framework for distributed reinforcement learning. In 2016, we got Double Q learning and the dueling architecture. Finally, in 2019, DeepMind published R2D2. The name Recurrent Replay Distributed DQN actually tells you a lot about the architecture of the agent. Recurrent Replay Distributed DQN. So there's a recurrent component, a replay component, and it leverages distributed RL. And this is all built on the core DQN algorithm. The R2D2 also incorporates double Q learning and the dueling architecture, which I'll talk about more later. Before we start diving into the papers, I'm going to introduce basic reinforcement learning concepts so that you understand what I'm saying. And well, because it's hard to understand reinforcement learning papers if you don't have that foundational knowledge. So what is reinforcement learning? Reinforcement learning is a subfield within machine learning that seeks to produce agents that learn by performing actions on an environment. The goal of the agent is to maximize its expected reward by learning a policy, which we denote as pi. I'll define what pi is later, but essentially it just informs the agent on what actions to perform in order to get the most reward. The following image illustrates the typical interaction between an agent and its environment. In a single time step, the agent performs an action on the environment, and the output of the environment is a reward for taking that action and the next state. Next, I would like to dive deeper into how the environment is modeled. So typically the environment is modeled as a Markov decision process, or an MDP. And an MDP is a general mathematical framework that models decision making. An MDP contains a set of states, actions, rewards, as well as a dynamics model. A dynamics model can be represented with a joint probability distribution over the next state and the reward, given the current state and an action taken in that state. If you have the dynamics model, it is possible to come up with the optimal set of actions to take, such that the agent will be able to maximize its reward. But typically the dynamics model is unknown to us, but it can be something that is learned. The following is an example of what an MDP may look like. From the states, you can take actions, and those actions can lead to other states. The numbers on the black edges are probabilities of ending up in a particular state after taking a particular action. And the numbers on the orange squiggle represents the reward. So now I'll define the previously mentioned policy, which we denote as pi. Generally speaking, the policy will tell you what action to perform in each state. The policy can be a deterministic function that takes in a state and outputs an action to take in that state. The policy can also be a stochastic probability distribution over all of the actions you can take from that state. We can also define an optimal policy, which we denote as pi star, which tells you the best action to take in that state in order to maximize the reward. Thus, our goal in reinforcement learning is to find this optimal policy. In reinforcement learning, we define two important functions called value functions. The first is the state value function v of s, which represents the value of a state, or the action value function, or q function, which represents the value of taking a particular action in a particular state. Intuitively, these functions tell you how valuable a state is, or how valuable taking an action in a particular state is, and then following the policy pi thereafter. To actually define these functions, we first need to define something called the return. So the return, which we denote g sub t, is simply the sum of rewards following time step t until the episode has terminated. So now we can find the value functions with the following expectations. The state value is equal to the expected return given the state, and the action value is equal to the expected return given the state and action. And just like how we had an optimal policy, we also have optimal value functions, which we denote with v star and q star. And if we find the optimal action value function, we can easily find the optimal policy by taking the argmax over the action values. So next we have the Bellman equations, which is just a way for us to rewrite the definition of our value functions into a recursive form. So below we have the Bellman equations for the Q function, and there is a similar analogous equation for the state value functions. In the first equality, we have the definition of action values, which is the expected return. The second equality arises from the fact that g sub t is equal to the immediate reward and the return at the next time step, followed by the linearity of expectation. The third equality is just taking the expectation over the policy, which utilizes the dynamics model I mentioned earlier. From the third equality to the fourth, notice that we have the expectation of the return at the next time step, given the next state and action. And while this is just the definition of the Q function for the next state and action. Similarly, we have the Bellman optimality equations, which rewrites our optimal value functions into a recursive form. So the optimal action values is equal to the expected immediate reward for taking action A in state S, plus the expected maximum action value of the next state over all possible actions. This equation will be important later when we define the DQN algorithm. So next I'll talk about the field of deep RL. Recall that our goal is to find the optimal value functions or the optimal policy functions, but the problem is that these functions are complicated and hard to find exact definitions for. However, we can use nonlinear function approximators such as neural nets to represent these functions. To do so, we need to parameterize our value functions or policy with parameters theta. And if we're given a target like in supervised machine learning, we can define our loss to be the expected difference between some target and the function we're trying to estimate. In this case, it is the Q function. An ideal target for our Q function would be the optimal Q function, or Q star. Then we can optimize this loss using gradient-based algorithms like SGD. The problem is that in RL, we're not given the target Q star, but we'll see later how DQN defines a target. Finally, we've built enough of a foundation of reinforcement learning to start diving into the literature. First is the popular DQ network, which was introduced by DeepMind in 2013 and gave rise to DeepRL. The agent was trained to play on 7 Atari games, and the results were that it was able to outperform all previous approaches on 6 of the games and surpasses a human expert on 3 of them. So relative to what we can accomplish today, this isn't that amazing, but back in 2013, this was a pretty big deal. However, I should note that this was not the first time nonlinear function approximation has been combined with RL. People have tried in the past, but it has often led to instability or divergence when training. So DeepMind introduced 2 techniques to deal with this issue. The first being experience replay and the second being a target network. So let's talk about the architecture behind DQN. DQN uses a shallow 5-layer CNN, which we call the behavior network, to approximate the Q function. The input to the CNN is 4 frames of an Atari game, and the output are the action values in that state. To understand why we need 4 frames as input, consider the single frame of the breakout game on the right. From this single frame, we are not able to tell which direction the ball is moving, and this information is critical in determining the correct action to take. And so, the input is 4 frames so that we are able to capture the velocity of moving objects. Next, we have the experience replay, which was used to stabilize training, and it can be thought of as a data set of experience. So as the agent interacts with the world, we store those interactions into the experience replay, and then when we want to update our loss, the agent uniformly samples batches of data from the experience replay and then optimizes our loss with respect to the batch. By randomly sampling from the replay, this decorrelates the data and stabilizes training. Next, we have the target network, which is a duplicate of the behavior network, whose parameters are held fixed between updates to stabilize training. After C time steps, the parameters of the behavior network are copied into the target network. So we denote our behavior network as the typical Q function, and the target network almost the same as the behavior network, but with the superscript minus sign on our parameters theta. This indicates that the parameters are held fixed. Now that we have defined the target network, we can now define the loss function for DQN. Recall that an ideal target for our loss would be Q star, but this isn't given to us. And recall that our Bellman optimality equation for Q star was the following. The DQN algorithm says to use the target network as an approximation to Q star. Thus, the algorithm is the expected squared difference between our target network and the behavior network. But notice that our target, the immediate reward plus the maximum over the target network, is written in the same form as our Bellman optimality equation for Q star. So the following diagram illustrates our DQN algorithm. Our Q networks are first randomly initialized, and from the network we get an action to take by performing an argmax over the Q values. This generates an experience tuple which gets stored in the replay memory. To make an update, our networks will sample a batch of data from the replay memory and compute the loss and the corresponding gradient. We then make updates to the behavior Q network on the left, and every n updates we copy the parameters from the behavior network to the target Q network on the right. In 2015, Halsknecht and his co-authors improved on the DQN algorithm by replacing a fully connected layer with a recurrent LSTM layer. Doing this enables the ConvNet to learn long-term dependencies. This allows the DQN to take as input a single frame due to the memory effects of incorporating a recurrent layer. So instead of needing 4 frames as input, we now only need a single frame. This idea generalizes the DQN to allow us to better deal with environments modeled as a partially observable MDP or POMDPs. Being able to generalize to POMDPs is important because real-world problems often feature incomplete information. So in 2015, Schall and his co-authors introduced prioritized experience replay. Recall that in the original DQN, they had an experience replay in which they uniformly sampled data to train the behavior network. Schall and his co-authors introduced PER, where instead of uniformly sampling from the database, they prioritized the experience samples that would give the network better learning progress. And intuitively, it makes a lot of sense to replay states in which the agent has struggled, rather than states the agent finds easy. To determine which experiences to replay, they rank samples based on the temporal difference, or TD error, which we denote as delta. And so the TD error is simply the difference between the target and our behavior network. And again in 2015, Nair and his co-authors introduced Gorilla, which is short for General Reinforcement Learning Architecture. And it is a framework for distributed reinforcement learning, and the results lead to approximately 10 times training speedups over a vanilla undistributed DQN. So the architecture consists of 4 main components: as parallel actors that generate new behavior/experience. It has parallel learners that get trained from stored experience. It has a distributed store of experience, and a distributed neural network to represent the value function or policy. The parameters are distributed via a central parameter server. So in vanilla DQN, you had a single actor and a single learner that's sampled from replay memory. But in distributed DQN, you have many different actors with their own environments on different machines, as well as many different learners that sample from a distributed replay memory. We also have the central parameter server, which represents the distributed network. The job of the parameter server is to apply the incoming gradients from the learners and to send the updated parameters of the model to the Q networks in the actor and the learner. The parameter server can be sharded across many different machines, and different shards are responsible for updating a subset of parameters that are independent of other shards. In 2016, Hasselt and his co-authors introduced WQ learning. So recall that our DQN loss function, where we have the expected difference between our target network and our behavior network, with the target network being the Q function represented with theta superscript minus sign, and our behavior network is the Q function without the superscript. So we're taking the maximum of our target network over all possible actions, and recall that our target network is an estimate of the optimal Q function. So this could lead to something called the maximum bias problem, which says that taking the maximum over estimated values and using it as an estimate of the maximum value can lead to a significant positive bias or overestimation. Essentially, we're using the target network to both select an action by taking the maximum over all actions, and to evaluate the value of taking that action by plugging in that maximum action into the Q function. The solution is to decouple the action selection and action value estimation by using 2 separate Q networks. But recall that the DQN algorithm already has 2 Q networks, the behavior network and the target network. And so we can use the behavior network for action selection and the target network for action value estimation. So instead of taking the maximum over the target network, we can use the double DQN algorithm, which says that we can select an action by taking the argmax over the behavior network, and then using the target network to evaluate that action. Next, we have the dueling architecture by Wang and his co-authors, but first I will have to define the advantage function. So the advantage function simply tells you the relative advantage of taking a particular action at a state compared to other actions, and it is defined as the difference between the action values and the state values. So Wang and his co-authors improved on DQN by creating two separate streams in a network, where one stream would estimate the advantage values and the other stream would estimate the state values. And from these two streams, we could find the action values or Q function by simply adding state values and advantage values together. In the image, the top network is the vanilla single stream DQN that directly outputs the action values. And in the bottom network, we have two separate streams that join together to produce the action values. However, they actually don't generate the action values in the naive way of adding the values together. They first subtract from the advantage values the maximum advantage value, or alternatively subtract the average instead. The reason for doing so is to overcome the identifiability issue, which means that given the action values Q, we aren't able to recover the state values and advantage values uniquely. The benefit of the dueling architecture is that we can learn which states are or are not valuable without having to learn the effect of each action for each state. The intuition is that sometimes all actions have no effect of the value of a state, and at that point it's better to just learn the state values instead. Finally, we have reached our destination and have covered everything relevant that has occurred prior to the R2D2 paper by DeepMind. So first, the R2D2 architecture, which is nothing more than combining all of the previous works into a single network architecture. To summarize, we had a recurrent DQN that utilized double Q learning and the dueling architecture. The network sampled from the experience replay, prioritizing certain experiences over others, and they also leveraged distributed computing. And the results were that the agent quadrupled the previous state-of-the-art on Atari 57, which is a popular benchmark in RL that consists of 57 Atari games. And it was the first agent to exceed human-level performance in 52 of the 57 Atari games. So on the left, you can see the median score of 2000% is about 4 times better than the previous agents, and the agent performed approximately the same as the state-of-the-art on another benchmark called DMLab 30. On the right, you can see at the 500% score, it can match the performance of the previous state-of-the-art Apex agent with 10 times less training time. Okay, thanks for watching.